there you go. So we are starting block number 3. And well, the idea here is to discuss three-phase OPF. So you already went through this to some extent with Steven, so I'm not going to go into the super details. I want, again, to focus more on the lessons that we have learned within my research team, the researchers that have worked on this, when we actually apply this to large-scale realistic implementations, all right? So there are many things that sometimes are totally dismissed by a lot of research groups around the world for different reasons, okay? But eventually, if we want the OPF to be something that will be adopted by industry, we need to look at how they might implement it and all the challenges that they're going to face, right? So I'm not going to talk about network modeling anyways, as I was doing this in the morning. That's a big challenge, right? Even just to run a power flow, forget about the multi power flow. But we're getting now into the details of the three-phase. So not the availability of data, but the fact that we need to move to three-phase. And not just that, also, there are many other aspects related to, well, the scalability that I was mentioning, there are aspects of fairness and practical implementations as well. So that's what we're going to do during the next 40-ish minutes. So we're going to discuss now is OPF for operations. So before we were discussing just planning and this AIMS tool that hopefully you will find useful to play with. But now we're going to discuss really the operation aspects. And well, what are the mathematical considerations? What are the practical considerations we need to have? What is the essence of the three-phase OPF, which is essentially, really, we have three phases, and then there's a mutual impedance between the phases, and then therefore there are interactions among the phases. That's it. That's the basics. A three-phase OPF, right? It's not complex, really. The only problem is that it just makes the whole problem much larger, and that brings other challenges, of course, for the formulation. Now, when we get into the mathematical aspects, then it gets interesting, because that's what you were doing as well with Steven. You know, you were going through different relaxations, you know, of the OPF. I'm not going to go through all those details. I'm just going to show you two implementations, you know, a quadratically constrained OPF and a linearized OPF. These days, we're using the linearized OPF in my team for everything. It's proven to be extremely scalable, extremely fast, and we're very happy with it. So much that, of course, you know, what we're going to discuss in terms of scalability, fairness, and necessary adaptations is all using the linearized OPF. That we will demonstrate with the Australian case study. For the kind of comparison between the quadratic constraint OPF and the linearized OPF, we're going to use a UK case study as well, another quite large network. All right, so let's continue. So this is a slide I already presented before, so this is just to remind us what do we mean by ACOPF for operation. So the idea is just to manage DR and network elements. And this is important because it's not just about managing DR, sending settings to PV systems or charging points or batteries. There are controllable elements in the networks, right? So we have the LTCs, we have the capacitor banks, we have voltage regulators, we have switching devices, so we can reconfigure the topology as well if we want to. So there are many things that can be done and need to be explored as well. Yes, we need a lot of infrastructure to make it work. Yes, we need the corresponding network models. We need data. Yeah, that's true. We discussed that already. So now we're getting more into the math and other aspects, assuming that the data is there and then that the network models are there as well. Okay. Of course, as I was mentioning earlier, doing this modeling in three phases is extremely important. And then, of course, not just that, you know, then you need to model in details, you know, your controllable and non-controllable DR, and then your controllable and non-controllable network assets, and any other aspect that you need. Okay, so when we talk about operation, we're talking about a process by which, for instance, perhaps you're just checking, assuming that you're checking voltages, right? So if that's your problem that you're really so concerned about. So the moment that you see a voltage problem, then you trigger, you know, the OPF to find settings, you know, that's it. Another option is that you do this every 5 minutes, every minute, and then you're always checking, and then or always triggering the OPF, you know, just to find the best setting. It depends on what you want to do, all right? So there's no single answer in how to implement things, but definitely in the context of operations, we're really definitely talking about seconds to minutes, all right? We're not talking about 50 and 30 hours or whatever, minutes or hours, you know, this is just not operation, right? So this needs to be real or near real time. And that, of course, creates its own challenges. Now, from a mathematical consideration, and they are just kind of to reflect as well on what you have learned in the last couple of days. There are different ways, of formulate your OPF. All right. You can argue there is a perhaps a best way or not. It will depend on the problem that you have. It depends on the network. For instance, some networks, as much as you will always hear that distribution networks are radial. Not all of them, all right. Some of them are actually loops, or what some people call weakly meshed, which means there are not so many loops, there are not many interconnections, but still there are some connections. So it all depends on the nature of your problem, of your networks, and one formulation might be better than others. It depends on the DER that you're modeling as well. Again, some formulation might be better than others, and what it means is that we just need to test. That's it. So from a modeling perspective, you can have the bus injection model, or you can have the branch flow model. The branch flow model is what you were actually using a lot with Stephen, for instance. How do you model, for instance, certain aspects? So you can use polar coordinates or rectangular coordinates. So when you look at rectangular coordinates, we're talking about, so P plus JQ, all right? But you can use angles as well, with polar coordinates. So how do you want to do it? So it depends. Again, one will have certain advantage, mathematically speaking, than the other, depending on the context of each problem. And then, of course, depending on how you are formulating the whole thing, you have a nonlinear program, you have a semi-definite program, you can have a convex realization, you can have a linearization. Sometimes they use S, sometimes they use Z. S is for British and certain. So there are many things. What is the best? Again, it depends on your problem, and you need to explore, what is the best formulation for your problem. How an OPF will be used by a company here in Australia might not necessarily be the same thing, that they are using it for another company in China, right? So it really depends. Now, so how do you choose them? Well, what is the most suitable one for your network? So some apply for radial networks only, as I mentioned. Some of them will apply, for mesh networks as well. So do you want to have that? Well, if you don't have any single mesh network in your region, why would you bother? Just keep going with the radials, with the formulations for radials. So what is the suitable speed that you're expecting from? Some formulations will give you faster results, perhaps less accurate than others. All right. Having discrete variables. How are you modeling your on-load tap changers? On-load tap changers are discrete, because are taps. 1 tap, 2 taps, 3 taps. How many taps you have there? Capacitor banks, they are staged as well. Can be on and off, but it can be different stages as well. So again, discrete variables. So how are you using your discrete variables? So when we talk about disconnection of electric vehicles, it's on and off, correct? So again, so these are discrete variables. How are we considering them? So this creates massive differentiation in terms of the problem, because it can make the problem much more complex. So you have a mixed integer linear program or mixed integer nonlinear program, for instance. And how accurate your results need to be as well. That, of course, that accuracy will depend on the nature of your problem. So if we're talking about, for instance, voltages, I mean, the reality today is that voltages of our homes, forget about renewables, right? Forget about photovoltaics. They already were all over the place, all right? So I know that, for sure, for many years. Our voltages in many places, sometimes are a little bit outside the limits, but we don't complain because our devices today at home, they are pretty robust with respect to voltages. It's not like the old teles that with lower voltages, the image was going to go smaller, or you could see, issues with your light bulbs that are incandescent bulbs. And then, of course, the voltage reduces, the light reduced. Now, today, we don't have that. So we don't see really that our voltage is too high or too low. So therefore, what is accuracy, all right? What is accuracy at the end of the day? Is having customers with problems. What is a problem? Is it really 10% above your nominal? I mean, like what we use here in Australia? Or is it okay to be 11%? What's the problem with that? All right. So at the end of the day, there has to be a practical engineering mindset to accuracy. All right. There's no point in trying to do a real-time OPF that is 100% accurate with what should be happening mathematically, you know, and the engineering problem, when actually it's going to be applied 10 minutes from right now, and in 10 minutes the demand already changed and the corresponding generation already changed. So what's the problem? What is the benefit of being 100% accurate from a calculation perspective when actually you are applying 10 minutes later? It's silly, isn't it? Correct. So the engineering aspect, the engineering application is as important as your formulation. So all these decisions have to have a very, very strong input from how you are going to apply it and what you're expecting from this. All right. So from a practical aspect as well, there are other things to discuss, right? So what we have is, for instance, the scalability of your OPF. So you have the fairness of the corresponding optimization problem that you are dealing with. And there are other adaptations that we need to consider. So let's start one by one, all right? So when we look at low voltage feeders and the medium voltage feeders and all the different interactions that we might have, so this plot here is trying to show you that, you know, that we have here the voltages, you know, from the primary substation in the medium voltage, they don't increase much with high penetration photovoltaics, but look at the low voltage values, you know, they are outside the limits here being, you know, 1.1 here in red. So what we're trying to say is that if you do not model your low voltage, you are not going to quantify what is going to happen to end customers, because that's where the residential photovoltaic is. However, if you model both the medium voltage and low voltage, then you have a big problem. And that means that your OPF has to be scalable enough, all right, for these massive networks that now are having multiple voltage levels, let alone the three-phase aspects, of course, right? Now, if we move into how you are actually formulating your optimization. So we were talking about settings, and we are going to discuss this a little bit as well in the next block with operating envelopes. But we were talking a lot already, you know, some questions there about export limits, you know, what will be the export limits that will have the voltages within the limits, for instance, you know, on the asset congestion, again, to the non-asset congestion, you know, the thermal utilization of the assets within the limits. Yes, we can calculate settings, guys, for all the different PV inverters or, you know, the charging of the batteries, whatever you want. But how do you differentiate the settings that you send to a house that is at the very end of a feeder and the house that is closer to a transformer? The house that is at the very end of the feeder, because of the impedance, any injection that does or any absorption that does will create a much larger effect on voltages. And then therefore, from a mathematical perspective, if you want to choose between the house at the very end of the feeder and the house at the very beginning of a feeder, you want to give priority to the house at the very beginning of the feeder because you can inject more power if that's what you want. But then that means that the other one will actually be affected massively, or perhaps not even, you know, being able to export anything. So that is fairness, because at the end of the day, we're talking about houses here. We're talking about people that bought their photovoltaic system or the electric vehicle, their battery, whatever it is. How do we implement fairness here? That is not easy, because being fair also means that you might not be necessarily very efficient. So we will discuss that as well. And there are other aspects. Temporal coordination is very important. So we're talking about operation, you know, of networks, and the networks already have elements that are totally decentralized. I've been talking a lot about all of the changers, you know, the primary subs, capacitor banks. They are most of the time in most countries totally decentralized control elements. You have a remote connection, so if you need to control them, you can, but they are always operating locally. So they are checking their voltages. For instance, an on-load changer is checking a voltage at the bus bar of the primary sub, or even if it is a remote voltage, the decision is all local, right? And the process is all local. Capacitor bank normally, you know, will be just checking whatever is the power factor or the voltage or whatever it is, again, at the connection point of the capacitor bank, and then we'll make decisions. It can be time-based, whatever, but again, it's local. So when we talk about OPF, sometimes we assume that we can control everything. The reality is that sometimes we could, sometimes we cannot. So how do we actually consider all these elements that have a local control? Okay, Nando, but let's suppose that we can actually control them. Fine, you can control them, but there are delays as well. So an on-load changer literally has a physical element that changes the tap from one position to another. That takes 60 seconds, all right? because it's not just about the data arriving, it's just because it's a mechanical thing to do. It takes 60 seconds. It's not a beautiful power electronic thing, all right? So you need to consider those 60 seconds to avoid as well other things. So let's suppose that you send a command to PV inverters that are automatic pretty much, and then you send a command to the LTC. And then your PV inverters do something, the LTC hasn't done that thing in these 60 seconds, and then you have a voltage excursion. And this can happen the moment that you get into really tricky situations with wind farms or solar PV farms. So we need, the OPF to capture what is expected in the actual network. And that also requires considering potential delays or the nature of how certain elements behave once they receive a setting, okay? They are not all immediately doing what we expect, right? So these are practical observations that we're going to discuss. So from a mathematical perspective, there are many papers that we have written, and they're all there, in the Canvas, so you can go through them. So the essence of three-phase OPF. So before we start with the QC quadratically constrained OPF versus the linearized OPF. So just remember, the essence of the three-phase OPF is just considering the mutual impedances among the phases, and of course considering each of the phase. And in some cases, you have single phase customer, you have parts of the network that are just taking one phase, the other. You can argue like, Nando, but in reality, we have the neutral. Where's your neutral? Nando, where is the ground? We have neutral and ground. So yes, actually, in reality, if you want to be very, very precise, you should be modeling explicitly the neutral. You should be modeling explicitly the ground, all right? And actually, as a matter of fact, you should be modeling as well the grounding of the neutral, in the different points. But it gets to a point where the information is just not existent. And the benefits from having that sort of detail of the modeling is not that great. It might be important in certain circumstances. I'm not denying that. But I mean, it's about finding a trade-off. At the very least, if we're dealing with single phase, two phase, three phase customers, particularly in the lowest voltages, you need to go for a three phase OPF formulation. And the minimum is modeling them as three phases, even if the neutral is not being modeled explicitly, all right? But it could, and it will create a much larger problem, of course. But it could be modeled explicitly as well. Anything that you can model as a power flow, you can model it as an optimal power flow. But that's it. It's as simple in inverted commas as it is. But of course, then you need to adapt it to the corresponding formulation, of your optimal power flow. As a non-linear optimal power flow, everything that you're doing a power flow can be modeled, but then you need to readapt it, for whatever it is, your linearization, your quadratic constraint, whatever it is that you're doing, your relaxations, all right? But that's the basic. So it's just expanding equations, really. It's not, in a sense, it's not that complicated, but you have more equations, and then you have more adaptations to do. Now, when it comes to the quadratically constrained and linearized two-phase OPF, I think that, which is what we're going to present in the next slides, I think that what is important to mention is first the key network variables. In the quadratically constrained OPF, and well, the links to the papers to the more details are there in Canvas. And we were using complex voltages, all right? So the real and imaginary parts of voltages, and as well for the branch cards, real and imaginary parts. Whereas for the linearized, what we're going to use is is this correct? The square of the voltage. Man, this is the other way around. I think, guys, I make a mistake here. The square of the voltage magnitudes, the power magnitudes. Yeah, I think that this is the other way around. I guess I make a mistake here with this. I will update it. But in any case, the more important part here as well is that they are very capable. Yes, this is the other way around, guys. This is, I don't know why. Yeah, I made a mistake here. So the linearized is on the left. The quadratic constraint, of course, the quadratic is here on the right, is on the right, okay? But they are all very similar, I guess, that apart from the network variables, but in the mesh section. So the linearized OPF, the formulation that we have there, it doesn't deal with the corresponding mesh sections, all right? And that's something important. The quadratic constraint, it can deal with mesh sections. Transformer models, very special models can be done. Discrete devices, yes, of course, this one becomes quadratically constrained program, right? In the case of the quadratic constraint, and in the case of the mixed integer linear program, well, that's what a linear program becomes, a mixed integer when I'm going to put discrete devices. But they're relatively similar in capabilities apart from the mesh sections, all right? Now let's start with the quadratic constraint. No, actually, Yes, that was okay there. So in terms of the three-phase line model for the quadratic constraint, what we have is the voltages on the real part and then the voltages on the imaginary part. No, actually, it was correct. It was correct that slide. So this is just a formulation that is using the phases here. For each of the phases, you need to do it, and it becomes a massive thing. For the power to current conversion, what we use is, the voltage. This is the quadratically part, that we're using of the magnitude of the voltages. For the P and Q, they multiply by the real imaginary part as well. And then for the nodal current, the nodal power, if you want, but this is currents, is the balance of what is happening, with the generation. X is just used, for corresponding slack bus, really mostly. The loads, etc., are equal to the demand and the local currents that you might have, for the resources as well. So these are the basics of the building blocks of the quadratic constraint OPF. For the linearized three-phase OPF, this is, here is just including the transformer, but what you're going to find here is that what we have here is, well, for households and distribution lines, everything is kind of linearized in many ways. And then, well, these equations, I'm going to go through all the details, all right? But you will have all the different equations and all of these for the different phases as well. Now, the delta Y transformers is something that can be done not just in the linearized, can be done in the quadratic constraint as well. And well, you have the constraints, nodal constraints and the power balance constraints, of course. And the objective function, of course, if we want to compare these two formulations, have to be put in the same way. Otherwise, what's the comparison? Let's get into the responses, into the performance. In terms of the comparison one against the other, what we're going to use is this real integrated medium voltage, low voltage network from the UK. It's real, the medium voltage part. The low voltage part is coming from real low voltage networks, but not exactly connected to those transformers. So it's kind of a bit of a hybrid, if you want. But this medium voltage network has indeed these transformers, these 9 transformers. And what we put is here a real low voltage network, but not necessarily that was originally connected to this transformer. So, and we put as many as needed according to the size of the transformers. Now, interesting here, in the UK, these distribution transformers, that are transforming from 6.6 kV to 400 volts line to line, they're quite large. Okay, so this is not very typical in many countries. All right, so in the UK, you can see very large transformers as well, like these ones. So, and then therefore they will have many low voltage networks as well. So all of this is modeled. So we have 36 fully modeled low voltage feeders and 9 OLTC transformers here. So just to experiment with mixed integer kind of formulation, as well as the distribution transformers. This is not common, right? All of the changer technologies in the low voltage is not common, but we're exploring it here. And in total, what we have more than 2,400 residential customers that are single phase connected. So it's pretty large network. So we have more than 4,500 three-phase nodes, which means in terms of single phase nodes, well, you have 13,000. All right, so pretty large network. So let's see the first scenario here. There's a question here for Edwin. Dynamic behavior could limit the hosting capacity, in which cases dynamic states are needed. Yeah, dynamic behavior can actually be embedded as a constraint as well, Edwin. So as I mentioned, fault levels, harmonics. So if you can formulate what is the constraint, you can actually put it in the OPF as well. But dynamic aspects are not relevant to distribution networks in general, particularly the moment that we get into the low voltages and mid voltages, and we're looking at connection of electric vehicles or photovoltaics. It's not something that distribution companies deal with. Now, the moment that we're talking about dynamics, because of the higher distribution level, so for instance, 66 kV, and we're talking about a solar PV farm or a wind farm, and you need to comply with certain requirements that are involving dynamics, then therefore, yeah, it is important. So it depends again on the DR that we're talking about. A small DR, but dynamics are really not that significant, really, to be honest, to the distribution company, of course. Now, moving back to this scenario here, where we're going to test the quadratic constraint OPF and the linearized OPF. So 100% residential PV penetration. Well, the objectives are going to be to maximize renewable energy harvesting and also to minimize the number of tap changes, right? So we're going to extract as much by putting settings on the different PV inverters, okay? 100% residential PV penetration, that it's likely to happen, but the idea is to test, how well these formulations are going to work. So how are we going to check the performance of these OPF formulations? we're going to do first a snapshot analysis. So at the moment of noon, so maximum generation, really, and low demand. And then we're going to implement these settings from the OPF into the real network, which is an OpenDSS. So the idea is just to extract the settings as you would do in reality from the OPF and put them in your real network. So our real network is OpenDSS, as I was explaining, earlier. So from the OPF, we get the set points for the PV settings and the LTC, and then we see what happens in OpenDSS, and then we assess the performance, right? Because at the end of the day, the network performance is what matters, as I was explaining before, right? So in terms of these initial results for this particular scenario, what we are seeing here is the linearized OPF on the left, and the quality constraints. This is without LTCs and then with all LTCs. And then we have the different metrics, so the number of customers with problems. Remember these thousands of customers, transformers with problems, so congestion, line problems, congestion as well, how much PV generation we have out of the whole potential, because we're curtailing eventually, tap changes, and the solution time in seconds, right? So first thing that you can see is that in general, all of them have negligible constraint violations. So the moment that we implement this in OpenDSS, all the settings, using a second run in all the cases of the OPF, well, we're talking about 1.1005 per unit. So that's nothing. Okay, so that's a mathematical value that tells you it's above 1.1. That's nothing. Okay, as I was explaining earlier, we already have problems in our networks. No one complains. So in terms of asset utilization as well, here in red is 101. So that's 1% above the thermal limit. Of course, our assets can handle that much more than that. So in general, those let's say little issues are not really issues. Everything's fine. In terms of what we see of total generation because of the curtailment, if you compare the linearized OPF with the quadratic constraint, well, 71% of the potential generation, 70.9, 71, 70. So pretty similar. All right. Now, when we get into the on-load that changes, that's when it gets interesting as well. Because in terms of the solution time, when we look at without LTCs, well, the linearized is 12 seconds, the quadratic constraint is 5 seconds. But the moment that we look at the use of on-load that changes and the corresponding mixed interior problem that it creates, what we see here is that linearized OPF does it in the second run in 19 seconds, whereas the quadratic constraint does it in 300 seconds, so 5 minutes. So both are using the same solver, Cplex, all right, and the same PC, but this is just an example where you need to understand what is your problem and what you're trying to achieve. So if really you needed to use mixed integer, clearly, in this case, the linearized OPF is a good option. But if you didn't need that, well, you can use either. That's okay, all right? So that's why these performance assessments are very, very important. Now, then there was another scenario that we did here. That's okay. Christian is asking more insights on the second run. Yes, so the second run is not a warm start. So the first run starts with a warm start. The second run is started with the result from the first run. So yeah, you can call it a warm start, but I mean, the first run is warm start in terms of, voltages fall from 1 per unit and angles equal to 0 for the voltages, for instance. But then the second run uses a result from the first run. So yeah, it is a warm start in a way. All right, moving on. So the second scenario is the night, right? So there's no generation, okay? So at 10 p.m., there's demand, so you can still use the download that changes, of course, to minimize, in this case, network losses, and well, we're gonna as well do it in a way that we don't have many tap changes, all right? So the results here are similar losses and tap positions for the two formulations, but in terms of time, the linearized OPF is much faster than quadratic constraint, okay? And this is the effect of the discrete variables. If we remove the tap changes, the linearized OPF will be, and the quadratic constraint will be very similar, or even the quadratic constraint is slightly faster, right? So again, I'm not trying to advocate for the linearized or the quadratic constraint, or there are many other formulations out there. This is about understanding that the application, the engineering problem, has to drive the selection of the most adequate formulation, okay? There's a question here from Sarah. In the second run, how did we determine the time to reach some steady state? I'm not entirely sure what you mean by the time to reach. So the time that we're quantifying here, Sarah, on the first and the second, is the time until it reached an optimal solution. All right. So in some cases, you cannot guarantee. So it's not a global optimal, but the linearity is. The quality constraint, you can actually, well, it is a global optimal. You're using Cplex. So it is that. Of course, there's a limit in terms of the time that we're waiting, but it is. So time here is simulation time. Yes, that's the simulation time, Sarah. Yes, that's correct. So that's what I'm saying. This is extremely quick. So we're talking about the OPF is totally doable in seconds. But the moment that you have extra challenges, like for instance, the mixing tier of the LTC, that can be many things, like on and off of electric vehicles or whatever, it creates some challenges for the quality constraint. So this is simulation time. It is pretty fast for such a large network. Now, moving on to, okay, there's another question for Krishna. What is the difference in the optimal cost for simulation? What is the optimal cost, Krishna? I don't understand. There's no cost here. We're just trying to maximize generation. So we're trying to harvest as much as possible. So that's it. We're trying to minimize curtailment. So I'm not sure what you call cost. All right. So moving on in terms of key remarks from this comparison. So the proposed quadratically constrained OPF, more details are on the papers there, guys. And the linearized OPF formulations, they facilitate the active management there, right? So that's great. They work, all right? Their scalability is clearly demonstrated. They work. The speed is pretty good, but of course, the speed, it gets a little bit affected in the case of the quadratic constraint the moment that we have discrete variables. However, again, what happens if you actually needed to deal with mesh networks? The linearized OPF is not set up as we propose it in our papers. It's not set up for that, but the quadratic constraint is. So therefore, again, it depends on what is your problem, that you are dealing with. Okay. Now let's get to the other aspects. I have around 20 minutes, so it should be fine. So now that we have compared, these two OPF formulations, and the main message again is not that one is better than the other. It's that what is your problem? What are you trying to address? What are the characteristics of your network? That tells you what you should explore. All right. But even the moment that you actually decide to go for one formulation, because it's the most adequate for your problem and your network as well, you still have other challenges. All right. So scalability is kind of something that we were addressing, but we are continuing addressing it here again. Fairness is one that really doesn't matter what formulation you have. Fairness is really about how you define your objective function and how you actually consider settings for different customers. And that is something that goes beyond the OPF per se. It's really about how you create a formulation, not of the OPF, but of this objective function. And all the necessary adaptations, as I was mentioning, the delays, things, so all the practical engineering aspects that you need to consider. Because remember, solving the OPF is not the end of the problem. You need to move these settings to the real network. And by moving them, depending on the control cycle you have and how the different elements operate and they react to the new settings and how long it takes, you will have a very different outcome from what the OPF was expecting. So the OPF is just one building block of the whole thing, of setting up the implementation of such an optimization engine in a realistic environment, or in a real environment as well. So the case study we're going to use, or now we're moving to Australia. So this is a integrated medium voltage, low voltage network with around 9 megawatts of peak demand, more than 4,600 residential customers, 79 distribution transformers. And all of this means in terms of nodes, almost 30,000 nodes and that are going to be used here. So what we're showing here in this plot is just the medium voltage part, but with the low voltage part has been also modeled. There's a question from Krishna. Why can't we assume the tabs to be continuous variables like round tab? I mean, you can, Krishna, but again, you need to understand. So you calculate your optimal settings, for PV inverters by playing with the tabs that are continuous variables, you solve the problem. But the reality is that what is the setting that you're going to tell them to your on-load changer? Your on-load changer has discrete because it's a mechanical device. All right. So these days you have smart transformers in the low voltage actually that are use power electronics. So doesn't need to be discrete, but still, in the primary substation is discrete. If we're talking about capacitor banks, it's on and off or are different stages. Again, it's discrete. So you cannot force your mathematics to solve a problem that doesn't exist because the actual physical problem is discrete. Now, you can use it discrete, but then the moment that you take these settings and move it to the real network, you will have a very different output. So, but why were you bothering so much with optimization when your outcome in the real network is totally different because of the discrete nature of the devices? So it's entirely up to you, up to the distribution company to accept those challenges and say, yes, let's do the OPF in a continuous way, for these elements. And we accept the fact that we will never have the values that the OPF is telling us in terms of voltages and things or whatever it is that you're able to maximize or minimize, because the moment that the settings are going to the devices are discrete and they will never achieve what the OPF wants. It's entirely up to the distribution company to decide that that's acceptable or not. So that's the answer there. All right. Now, moving on with the medium voltage network, what we have now here with the medium voltage network is what we're gonna actually model all these, houses and things. Again, very similarly to the previous case study, where we're gonna have again the OPF exploiting, all the different settings and the flexibility, but these settings then will go into a network, into OpenGSS, so as to really measure what the OPF expects to achieve against what the actual network, in this case, model in OpenGSS, is going to do. And this assessment is important, guys, because exactly, as Krishna was saying, we can always focus on the mathematics of the OPF and make things work. It doesn't matter if it works from the mathematical perspective, when in the engineering perspective, when it's applied, it will not achieve what we wanted. So we need to find a trade-off, right? And for us to really assess this in a realistic way, we need to separate, the OPF settings from the actual network simulation, right? And this is what we're going to do again. So in this case, let me just, what is this? There's a question and answer here. Okay, let's click here. All right. So what we are going to do here is first assessment of accuracy and speed. And what we have here is different cases here at 1, 2, 3, 4, where we have flat stars, warm stars, and warm stars. So flat start is the flat star that I was mentioning. Yes, that's not a warm star, it's a flat star. So voltage is equal to one per unit, and the angles of the voltage is 0, and other elements, equal 0. Then flat start with second iteration, with 2 iterations. Of course, this is just using the previous one, and then just see what happens. And then warm start as well, just using the first flat start instead. So you have different ways of looking at this. The warm start here is using the SCADA values from the previous moment in time. So flat start from warm start is different in that sense as well. Anyways, so remember, because it's operation, you don't need to do OPF from flat start necessarily, because in operation you have the last results, all right, of voltages, currents, and everything, or not from the results, from the measurements. So you can put these measurements as your warm start as well in the first iteration. So this is the one that we mean, warm start first iteration. So if you compare this here, what we are saying here as these 4 cases is that the moment that you use your warm start values coming from SCADA, all right, in the OPF, you actually have a better performance of your results, all right? So this is across the different voltages of all the customers. And if you actually run a second iteration of the OPF, you even improve your results further. So that's great. So in terms of transformer utilization as well, what we have here is that we reduce that. So the errors are diminished, significantly as well, and that's great. So the OPF matches very, very closely with reality, particularly when we use the second iteration of the OPF, and particularly even more if we use the warm start when it comes from the SCADA data, and that's brilliant, right? So in total, you know, we're talking about seconds less than a minute, and that's fantastic. So this can actually work in terms of accuracy and speed. Now let's look at fairness as well. So if we look at fairness, then the thing here, as I was mentioning, is okay. So we were looking at using settings, you know, for photovoltaic systems, so people actually reduce their generation. Well, not people, but the inverters reduce the generation, because right now there's too much generation in the network, so we're sending settings. So one way of doing this is, for instance, okay, let's just say everyone is curtailed 10%. All right. Okay, that can be considered fair, right? There's another aspect of saying, well, no, just curtail those that are creating more problems. I don't know, because they are more sensitive, or just let the OPF decide. I mean, there are many ways of doing this. But then what is fair to customers? Because we're dealing with customers at the end of the day, and anything that we come up with that affects everything behind the meter. So we need to be careful. So how do we do this? We are not going to propose a specific way, just we're going to show here the different aspects of assessing fairness, okay? So what we have here, for instance, is different indices. So we have the PV harvesting index, which is essentially just quantifying, let me just put the graph here. So quantifying how much you are actually harvesting from the photovoltaic system. We have an energy export index, which is quantifying how much you're exporting to the grid, and a net benefit index that is looking at the monetary value for you're getting. Because if you are actually saying, oh, we're going to curtail all the photovoltaic systems, so you might be curtailing someone that is actually at that moment in time, because they're at home, consuming all the electricity, meaning they are not exporting to the grid, right? So you're curtailing someone that is not creating problems because they are actually at home. So how do you do this then? So so do you have to then send a setting that also considers what is the local demand? So there are many ways of dealing with this, but what we were trying to do with this particular paper, that the links on the canvas on fairness, is to really assess the different perspective, right? So it's not as simple as it seems, you know, to be fair. And what we're going to use for fairness is also the James Fairness Index, which is something that is used for communication purposes. So we just extracted that index here just to present that. So again, there are many ways of looking at maximizing, you know, how much we're going to extract from photovoltaics. All right, it's because of the photovoltaic generation itself. It's because of the energy that people are, or the export that people are doing, the net exports, or because of the net benefits in terms of, you know, the economic value to each of the customers. So we're going to create different OPFs for that. So we're going to create an OPF total, which is what we were using before, for instance, with the comparison of the quality constraint and the linearized. We're going to use an OPF generation that just looks at the generation. We're going to use an OPF export and OPF financial as well. So these are just different formulations. So we're going from super unfair to fair, but fair from different perspectives, okay? Because what is fair at the end of the day? So we're going to maximize, if we simply maximize the aggregate PV generation, it's not necessarily desirable, right? So, but at the same time, if we say, let's do it from a fair perspective or fairness perspective, okay, which one? Is it the economic perspective? Is the export perspective? Is the generation perspective? Which one, right? So what we need to understand is that as depending on the different locations for a similar demand, you will have different effects, all right? So here what we are showing is the different PV generation for different customers, one at the start of a low voltage feeder and another at the very end. And this is what I was mentioning earlier, you know, with fairness. So what we see here is the PV total that just cares about extracting as much as possible of the aggregated exports, will allocate to the customer at the beginning of the feeder, close to the distribution transformer, a lot of generation, so they can actually export throughout the day. But the house that is at the end of the feeder, that of course, you know, any little kilowatt that they inject will affect the voltages much faster because of the impedance. They will actually give zero exports, you know, to that, or zero generation, actually, as a matter of fact, to this particular house. And they have the same demand, all right? So is that fair? What would you say? Well, I mean, this is best for the system in the aggregate, you know. Well, yeah, but then is it fair for that house? Well, I don't think it's fair, actually. But then let's look at the other options that we have: OPF generation, OPF export, and OPF financial. In this case, in the OPF financial, We have almost similar values in the OPF generation, similar values, and the OPF export as well, similar values. So there are ways of finding some sort of fairness. And by fairness, what we mean is that everyone is treated equally. Of course, in this case, both have the same size of photovoltaic inverter and similar demand as well, right? So they're pretty much similar houses. Why would they have to be so different just because of their location? All right. So that's what we're trying to highlight here. Now, if we look at similar location and different demand, then we have different results, right? So we have results that are actually showing us something different because they might have the same, generation potential, same PV system, but because someone is locally consuming more electricity that day because they're at home, they are affecting less the network, all right? So forcing them to actually do the PV generation optimization or the export that supposedly were fair might not necessarily be that great because actually the financial one is what matters, right? So what we have here is that in this case, the PV OPF export is actually allowing to be higher because of the demand here. So depending on what you consider as data and whatever it is fair, you will have very different results. And well, it depends. At the end of the day, someone has to make a decision of what is fair and what are the considerations, But what we wanted to show is that fairness is something that has to be considered as well. There are a couple of questions here. Adding fairness factor in the objective function means you will get a multi-objective optimization when you're needing to carefully choose right? Well, there are different ways of considering this fairness objective. More details are in the paper, Guyan, but not necessarily it's a multi-objective function. It all depends on how you formulate it. David, the fairness quantification looks like a good opportunity for multi-objective optimization. Well, again, it's not a multi-objective optimization necessarily. It depends on the parameters that you consider. More details are in the paper. Now, moving on with fairness, so then we did this assessment, for thousands of customers, and we extracted the Jane's fairness index, all right, which is one of the fairness indexes that exists in the literature, typically used for communication purposes. Now, what we are seeing here are the different settings that you end up, all the curtailment actually that ends up being applied, to the different photovoltaic systems, and it all, changes depending on the different things. So that these fairness indices are being assessed for all the different customers, and what we have here is a table that show us what is actually happening. And with the OPF generation, the fairness index, when you actually consider the photovoltaic generation only, is 1. Of course, the OPF export only, and then you consider export is 1. So this is what you expect, that if you consider one objective, you will have 1 if the objective has been considered properly, right? But what it also says is if you use an objective such as the OPF total, and then what you wanted to assess is what is happening financially, well, it's not as fair as the financial, or it's not as fair as the export. So it's a relative comparison here. So all in all, the OPF total, as expected, is the least fair in all the metrics. However, the other metrics are not necessarily perfect, right? There are different trade-offs. So we're not advocating for one or the other. What is ultimately fair? It depends on whoever wants to make a decision. Is it a regulator? Here in Australia, the Australian Energy Regulator, for instance, who decides that will not be the distribution company necessarily, right? Because this affects customers. But what I'm trying to say here is that it's an aspect that has to be dealt with eventually, because in the next hour, we're going to talk about operating envelopes. And this is about, telling people that not people, but aggregators are managing the things of the people, how much they can do things. And if this is not done in a fair way, it can have implications as well. Now, finally, there's the adaptations of the OPF-based set points, all right? So this is what I was mentioning, that if you actually do something right now in your OPF, it doesn't mean that if you send a setting, it will happen immediately, in the next second. So there are delays, not because of communication. We're talking about delays because of the devices themselves taking an action to the corresponding new setting. Now, power electronics, they are immediate, but on-load changers, they take their time. Capacitor banks, they take their time as well. Well, not necessarily that much, but still, the OLTC is the one that takes more. If we're talking about solar PV farm or wind farm as well, at the higher voltage levels, they have ramping as well restrictions. They cannot just simply say, well, okay, I'm gonna move the pitch of the angle of my blades in 1 second. No, it takes a while. It's a mechanical process as well, right? And even if they could do it faster, there are requirements by which they shouldn't, all right? So there are ramping restrictions as well. So all of this needs to be considered. And what it means is that all these times need to be adequately incorporated in the OPF. And if you do it, then you will have an outcome as expected. If you don't, it might be very, very different. So, and this is what happens specifically as well with the unlock that changers, because what you have is normally, if you don't directly control the tabs, you will send a setting to the OLTCs, and then you need to wait for that setting to be enacted. But if you control directly the tab, which is the case here on the bottom, then you are able to say which tab to move. Now, that requires changing as well some relays in the corresponding unlock that changer, the primary sub, but it is totally doable. That can bring some benefits as well, because it means that you can do this. And in terms of the ramping of the distributed generation, well, I mean, you just have to follow the corresponding restrictions, but depending on the technology, it can be faster or can be slower. So this is just to show, what happens, if you actually use the adaptations and you don't use the adaptations. Without adaptations is on top, and what we see is these voltage excursions that I was talking about. So the OPF can be beautiful, but the OPF is not the end of the story. The settings need to move to the real network, and the real network will have some delays in their devices, how this is enacted, by the different devices. And this delay can create spikes. And these are the spikes that we don't want, because at the end of the day, what are we using our optimal power flow is to manage very well the network. And if it needs to be within those limits, then we're not doing a great job with our OPF. So that's where the OPF needs to be adapted to the characteristics of the corresponding devices, so as to really ensure that we don't have problems. That's the whole point that I'm trying to make. And more details are, of course, in this corresponding paper that are on in Canvas, of course, as well. Now, just to conclude, now finally I managed to finish on time, and then we have a tiny break. So dear orchestration, we need it eventually, right? And the OPF can help for sure, but there are practical considerations, scalability that I keep saying, fairness, which is the new one that I was mentioning, and implementability, which is the last one that we were just discussing, right? So we really need to consider these practical aspects if we want the OPF to be used eventually by companies. It is not just with the mathematics. We cannot stop in the mathematics. We need to look at the engineering problem. We need to look at how the OPF settings are going to be implemented, what are the corresponding characteristics of the devices that are going to receive these settings, so we can actually adapt the formulation of the OPF for a very, very realistic implementation. And going back to this comparison that I did in terms of the quadratic constraint OPF and the linearized OPF, I'm not going to say which one is better. It depends on the application, right? And the same thing with many other formulations. It depends on the application. You need to know what is application and what are the limitations of your OPF. Right, but of course the linearized OPF pretty good. But the moment that we get into mesh networks, well, it doesn't work. It will require some adaptations. So just to thank Michael and Luis, Osnet and which is in Northwest, they are part of this work, Manchester as well. And that's where I stop right now. I'm happy to answer some questions, but I'm stopping. Okay, now there's a question related to OPF, and I want to answer that live. So here's one. OPF here is one-time snapshot optimization. Correct. The input of OPF are current time t, warm start, and send set points to real t. Yes, but the optimization is under calculation. The system could change load. Yeah, that's true. That's true. Which means the set points send later, not automatically. Right. That's absolutely correct. Anonymous. How can we formulate the continuous OPF in multi-time stance, taking advantage of load their forecast? So yes, absolutely. So there are two things of adapting the OPF for particular. I mean, there's one aspect. The moment that you do control in very, very short control cycles every 5 minutes, the changes in demand and generation are not going to be so dramatic. All right. That's the first thing. They're going to be dramatic if you wait 1 hour. However, let's suppose that still you want to be more precise, because there will be changes. All right. Even if they are not dramatic every 5 minutes. So you can do an incorporation of the forecast. That means that if you incorporate the forecast, you either trust your forecast 100%, which you shouldn't, or you trust the forecast to the extent that the corresponding probability is also known. that a forecast will give you. And what you do is you create a stochastic OPF, which is essentially giving probabilities to the different potential realizations of your forecast. And then just solve the OPF for all the different cases. And then that's it. That the only challenge there is that makes the OPF as a problem a little bit bigger. And also a big problem there is to extract that forecast. So that's a big challenge on its own, having good forecasts per house. All right, that doesn't exist today. I mean, some people claim to do it, but it's extremely difficult. The aggregators cannot do it. They have some estimates, but it's not really good. It's actually very bad. So if your forecast of individual house is bad, I prefer just to assume that it's not going to change, isn't it? If it is every 5 minutes, so it's entirely up to you. But there are ways you can create an stochastic OPF, but then you need the forecast, and that will be a piece of information that it will be critical to have. I'm gonna stop here, guys. Thank you very much.